Welcome to the Marine Fuel course on ChiefEngineerLog.com, where we dive into the essentials of powering vessels safely, efficiently, and sustainably. There are different types of marine fuels available today on the market, and marine industry will go into a major change sooner or later, as a response to the continuous change of the environmental rules and regulations. Therefore, the marine industry, among other industries, must respond and adapt to the changing and more strict regulations and become more efficient with regard to fuel consumption and emissions. Many companies are researching and developing new types of fuels in liaison with engine manufacturers and shipyards. Some of the engine manufacturers strive to adapt and retrofit their existing engines to the new fuels when possible, as it proves to be more economically practical. However, new-built vessel will have to be equipped with new designed and versatile engines, which can be used on dual fuels or new different type of fuels. After 2020 sulfur cap compliance regulation, all conventional vessels are forced to use HFO plus scrubber or LSFO, and these fuels perform well on most parameters. There were some concerns about the availability of these fuels after 2020, but they are still significantly available than alternative fuels. The primary disadvantage of these fuels is their low environmental performance. Fuel for marine operations of marine fuels is comprising of heavy fuel oils, distillates, LNG, ammonia, hydrogen, methanol, fuel cells, and others. In the case of distillates, a distinction is made between marine gas oil, MGO, and marine diesel oil, MDO. Residual fuel oil accounts for the vast majority of the fuel oil used by the world's merchant fleet. This also applies to the vast majority of large diesel engines used on land. By definition, residual fuel oils are the byproducts of refinery processes that remain after the distillate or lighter fractions have been removed. These residues are complex mixtures that vary depending on the source of the crude oils processed and the refinery's complexity. Scrubbers incur high investment and operating costs, but these are negligible in comparison to the costs of alternative fuels. Fuel oil was initially derived from the residue of the atmospheric or vacuum distillation process in the early days of refining. By and large, the product entering the market for fuel oil was of consistent quality, with few issues. As demand for distillate products increased, refiners implemented secondary refining processes, altering the market characteristics of fuel oil. The secondary refining processes have some side effects like lesser amount of residual fuel, higher microcarbon value, stability and sediment problems, higher density and catalyst fines contamination problems. Individual country-specific product demand is extremely diverse and cannot be met solely through crude oil selection due to the sheer volume required. Additionally, within a single geographical area, a variety of crude oil sources and refinery process configurations are used. As a result, fuel for industrial and marine markets exhibits considerable variation in its properties on a global scale. While this has been the case for the most part throughout history, the variations can be more pronounced than in the past. The first step in the manufacture of petroleum products is the atmospheric distillation of crude oil into its major fractions. When crude oil is heated, the lightest, most volatile hydrocarbons evaporate first, followed by the heaviest, least volatile hydrocarbons. After cooling, the vapors are condensed back into liquids. A fractionating column is used to carry out this distillation process. The column is divided into chambers by perforated trays that condense the vapors and allow the liquids to flow into storage tanks at each stage. The crude oil is preheated to a maximum of 350 degrees to avoid thermal cracking. The residue from atmospheric distillation is sometimes referred to as long residue, and additional distillation at a reduced pressure and high temperature is used to recover more distillate product. This vacuum distillation process is critical for optimizing crude oil upgrading. The vacuum distillation residue, sometimes referred to as short residue, is used as a feedstock for further processing or as a component of a fuel. Unlike the fractionating column used in atmospheric distillation, the low-pressure vapors are condensed using a system of packed beds rather than trays. Refineries that rely solely on atmospheric and vacuum distillation are referred to as straight-run refineries, and the fuel oil produced is essentially either long or short-run residue. The residue percentage varies according to the composition of the crude processed. The residue is 28% for a typical light North African crude and up to 85% for a heavy Venezuelan crude. The proportion of products produced does not always correspond to the demand for them and is largely determined by crude oil. Here there is an illustration of typical refinery process. Additional refining processes were introduced to meet product demand. Apart from atmospheric and vacuum distillation, a modern refinery may also include secondary refining processes such as cracking, which may be thermal or catalytic. Thermal cracking is the oldest and, in theory, the simplest method of refinery conversion. It is carried out at temperatures ranging from 450 to 750 degrees C and pressures ranging from atmospheric to 70 bar. Temperature and pressure are determined by the type of feedstock and the desired product. At these elevated temperatures, the large hydrocarbon molecules become unstable and self-destruct. Another critical factor in the process is the length of stay. The thermal cracking process has three primary applications in modern refineries: visbreaking, thermal gas oil units, and coking. Visbreaking is the most critical process in the production of residual fuel oil. It is a relatively mild type of thermal cracking that is frequently used to reduce the viscosity of straight-run residual fuels. Typically, such fuels are extremely viscous and must be blended with a relatively high-value distillate to meet the finished product specification. Visbreaking significantly reduces the amount of distillate required as diluent or cutter stock, which can then be diverted to a more profitable product stream. A thermal gas oil unit's primary objective is to produce and recover the maximum amount of gas oil possible. In extreme cases, the residue's viscosity may exceed that of the feedstock. Coking is a form of thermal cracking that is quite severe. It is intended for the conversion of straight-run residues to more valuable products such as naphtha and diesel oil. Additionally, gas and coke are produced, and as a result, this process is not used in the production of residual fuel oils. There are numerous residues and diluents available in a modern refinery for the production of fuel oil. Typically, the fuel is made up of visbroken residue that has been diluted with cycle oils and trace amounts of other distillates. Here, the figure depicts the major feedstock, diluent, and residue streams in a modern refinery. The British Standard Institute was the first to issue a specification for ship fuels in 1982, BSMA 100. It was developed collaboratively by suppliers and engine manufacturers with quality and price trade-offs. The International Maritime Organization, IMO, initiated ISO 8217 Petroleum Products, Fuel, Class F, in 1987, which has since become the general standard. The standard makes a distinction between residue fuels, RMA, RMB, RMC, RMK, and distillates, DMX, DMA, DMB, and DMC. It categorizes residue fuels based on viscosity and establishes class-specific limits, maxima for density, flash point, pour point, coke residue, water, ash content, and sulfur content. Viscosity classes are defined as viscosity values of 30, 80, 180, 380, and 700 mm at 500 C. As it was anticipated that the reduction of the maximum sulfur content of marine fuels to 0.50 metrem% would lead to a transition in the nature of marine fuels and a revision of ISO 8217-2017. Not possible by 1 January 2020, ISO Pass 23263-2019 was developed to address fuel quality considerations in view of the implementation of the maximum 0.50% sulfur limit in 2020 and the range of marine fuels expected to be placed on the market. ISO Pass 23263-2019 addresses general considerations on the sulfur content and flash point of 0.50 mm%s fuels. The application of ISO 8217.2017 to these fuels, but also specific considerations which may apply to some of these fuels. In particular, kinematic viscosity, catalyst fines, stability, cold flow properties, wax formation, and ignition characteristics are addressed. As it was expected to see a higher variety of fuel blend formulations as of January 2020, and although compatibility is not a specification within ISO 82 ISO PAS 23263-2019 provides information on how to minimize the risk of incompatibility between fuels when commingling onboard is unavoidable, and how to evaluate compatibility. Important specifications to ensure reliable engine operation with residual fuel are: maximum density limit, important for classical purifier operation and to ensure satisfactory ignition quality for low viscosity fuel grades; maximum aluminum and silicon Al+I limit. In a complex refinery, HCO is used as a blending component. Mechanically damaged aluminum silicate catalyst particles of the catalytic cracker are not completely removed from the HCO stream and are found in mg/kg amounts in heavy fuel blended with HCO. In order to avoid abrasive damage in the fuel system onboard the vessel, it is necessary to limit the amount of Al+Si to a level which can be adequately removed by the ship's fuel cleaning system. Maximum total sediment aged limit. The stability of asphaltenes is deteriorated by the vis braking process, and instability problems can cause fuel purification and filter blocking problems, hence the need for a specification to ensure adequate fuel stability. With the introduction of lower maximum sulfur limits, more paraffinic product streams are used for the blending of these fuels, especially for low viscosity 0.50% sulfur residual type fuels. Attention should be given to the cold flow properties of the fuel intended to be used for a particular voyage. The ISO 8217-2017 specifications can also be applicable to fuels for stationary diesel engines of same or similar make as those used for marine purposes. The most important marine fuel properties listed under ISO 8217-2017 are: catalyst fines. Heavy cycle oil is used worldwide in complex refining as a blending component for heavy fuel. Mechanically damaged catalyst particles, aluminum silicate, cannot be removed completely in a cost-effective way, and are found in blended heavy fuel. Fuel pre-cleaning onboard ships has a removal efficiency of approximately 80% for catalyst fines. In order to avoid abrasive wear of fuel pumps, injectors, and cylinder liners, the maximum limit for Al+Si is 60 mg/kg for RMG and RMK category fuels since 2010. CCAI. The Calculated Carbon Aromaticity Index, CCAI, is only applicable to residual fuel oils and provides an indication of the ignition delay of a fuel oil. The CCAI is calculated from the density and viscosity of a residual fuel oil. Some engine manufacturers specify CCAI limits for their engines, depending on engine type and application. Ash. The ash content is a measure of the inorganic incombustible components present in the fuel, either as inherent to the fuel or as contamination. Carbon residue. Carbon residue is determined by a laboratory test performed under specified reduced air supply. It does not represent combustion conditions in an engine. It gives an indication of the amount of hydrocarbons in the fuel, which have difficult combustion characteristics, but there is no conclusive correlation between carbon residue figures and actual field experience. The microcarbon residue method is specified by ISO 8217. Acid number. All fuels have a naturally occurring acid number. However, fuels with high acid numbers arising from acidic compounds can cause accelerated damage to large diesel engines, especially the fuel injection equipment. However, fuels manufactured from naphthenic crudes can have an acid number exceeding the maximum specified in ISO 8217-2017 but still be acceptable for use. Currently, no identified correlation between the acid number of a fuel oil and its corrosivity exists. Cetane number. Cetane index is only applicable for gas oil and distillate fuels. It is a measure for the ignition quality of the fuel in a diesel engine. The higher the RPM of the engine, the higher the required cetane index. The cetane index is an approximate calculated value of the cetane number, based on the density and the distillation of the fuel. The cetane index is not applicable when cetane improving additives have been used. Cloud point, cold filter plugging point. The cloud point is defined as the temperature at which wax crystals start to visibly form in the fuel, and a transparent fuel becomes cloudy. The cold filter plugging point is the lowest temperature where the fuel of a set volume drawn, by vacuum, through a standardized filter within a specified time, still continues to flow. Marine distillate fuels with a higher content of heavier end paraffins may lead to cold flow operability issues, as wax settling can occur even when the pour point specification is met, when a ship is operating in colder climate regions, or when a ship is having restricted heating capabilities for their distillate fuel tanks. Therefore, ISO 8207-2017 requires for winter grades of DMA, DFA, DMZ, and DFZ the cloud point and cold filter plugging point to be reported. The International Council on Combustion Engines, CIMAC, has developed a guideline on cold flow properties of marine fuel oils. This guideline aims to provide ship's crews with a better understanding of a fuel's cold flow characteristics, which have become more important but are often overlooked when storing and handling distillate fuels. Density. The official unit is kgm3 at 15 degrees C, while kgl at 15 degrees C is the most commonly used unit. Density is used to calculate the quantity of fuel delivered. The density gives an indication of the ignition quality of the fuel within a certain product class. This is particularly the case for the low viscosity IFOs. The product density is important for the onboard purification of the fuel. The higher the density, the more critical it becomes. Kinematic viscosity. Kinematic viscosity is a measure of the fluidity of the product at a certain temperature. The viscosity of a fuel decreases with increasing temperature. The viscosity at the moment the fuel leaves the injectors must be within the limits prescribed by the engine manufacturer to obtain an optimal spray pattern. Viscosity outside manufacturer's specifications at the injectors will lead to poor combustion, deposit formation, and energy loss. The viscosity of the fuel must be such that the required injection viscosity can be reached by the ship's preheating system. For distillate marine fuels, most large diesel engine builders request a minimum viscosity of the fuel before the fuel injection pump of about 2.0 mm/s CST. Hence, for distillate marine fuels with a minimum viscosity of 2.0 mm/s CST at 40 degrees C, according to the ISO 8217-2017 standard, cooling or chilling may be required to maintain the required minimum viscosity before the fuel injection pump. Flash point. Flash point is the temperature at which the vapors of a fuel ignite, under specified test conditions, when a test flame is applied. The flash point for all fuels to be used in bulk onboard vessels is set at Penske Martin's closed cup 60 degrees C minimum, SOLAS agreement. DMX, a special low cloud point gas oil, may only be stored on board in drums because of its 60 degrees C flash point. Pour point. Pour point is the lowest temperature at which a fuel will continue to flow when it is cooled under specified standard conditions. Straight-run heavy fuels have a pour point typically in the plus 120 degrees C range, while high-sulfur bunker fuels from a complex refinery generally have pour points below 0 degrees C, range 10 to 20 degrees C. This can lead to problems if a vessel receives high pour, straight-run, bunker fuel, and the bunker fuel tanks are not completely or only before the fuel transfer pump heated. With the introduction of lower maximum sulfur limits, more paraffinic product streams are used for the blending of marine fuels with a maximum sulfur content of 0.50% and therefore can have higher pour point as well. Vanadium and nickel are elements found in certain heavy fuel oil molecules, asphaltenes. Upon combustion, vanadium oxides are formed, and some have critical melting temperatures. The most critical are the double oxides, sulfates with sodium. Some countries have implemented maximum Ni concentrations for inland use of heavy fuel. The elements calcium, zinc, and phosphorus are considered fingerprint elements of used lubricating oil. Hydrogen sulfide, H2S. H2S is a highly toxic gas and exposure to high vapors. Concentrations is hazardous and can be fatal in extreme cases. It is naturally present in crude oils and can be formed during the refining processes used to produce the fuel. H2S can also evolve from the fuels in storage tanks, barges, and customer tanks. Residual fuel oils can contain varying levels of H2S in the liquid phase, and in some circumstances, higher levels of H2S can be observed in marine distillate fuel oils. H2S can be present in both liquid and vapor phase, and the partitioning between the liquid and vapor phase depends on a number of factors, e.g., fuel temperature, viscosity, level of agitation, etc. The 5th edition of ISO 827 defined a liquid phase H2S limit of maximum 2.0 kg as measured by test method IP 570 as of July 2012. This limit intends to provide an improved margin of safety. The limit alone does not constitute a safe level or eliminate the risk of very high levels of H2S vapor being evolved in enclosed spaces. AlpSi, aluminium and silicon. The ISO 8277 prescribed test methods are ISO 10478, or IP 501, or IP 470. Only these methods and fully equivalent methods from national standardization organizations should be used. A former industry-wide maximum limit for catalyst fines in heavy fuel was defined on Al alone, 30 million kg. The ratio between Al and Si can, however, vary considerably between different types and manufacturers of aluminum silicate catalyst. This is why the test measures the sum of Al and Si. In practice, the two ways of limiting the catalyst fines content in heavy fuel give the same degree of protection. Water in fuel is a contaminant and does not yield any energy. The percentage of water in the fuel can be translated into a corresponding energy loss for the customer. Water is removed on board the vessel by centrifugal purification. If after purification, the water content remains too high, water vapor lock can occur and pumps can cut out. If water-contaminated fuel reaches the injectors, combustion can be erratic. Water in fuel that remains standing in lines for a longer period can cause corrosion. The sulfur content of a marine fuel depends on the crude oil origin and the refining process. When a fuel burns, sulfur is converted into sulfur oxides. These oxides reach the lubricating oil via the blow-by gas. These oxides are corrosive to engine piston liners and must be neutralized by the cylinder lubricant. Marine engine lubricants are developed to cope with this acidity. If the correct lubricant is used, the sulfur content of a marine fuel is technically not important, but may have environmental implications. Since the early 2000s, regulations to reduce emissions from shipping are in place and have been tightened over the years. The increasing restrictions on marine fuel sulfur content have shifted the primary blend target of marine fuels from viscosity and density to sulfur. MARPOL Annex 6, first adopted in 1997, limits the main air pollutants contained in ships' exhaust gas, including sulfur oxides, SOx, and nitrous oxides, NOx. In 2008, the revised Annex 6 to MARPOL 7378 was adopted and required the sulfur content of any fuel used on board ships not to exceed 350 min-m% as of 1 January 2012. The revised Annex 6 also restricted the sulfur content of fuel oil used on board ships operating within an emission control area, ECA, to 0.10 mm% as of 1 January 2015. The revised Annex 6 also included the requirement to further restrict the sulfur content to 0.50 mm% on and after 1 January 2020. However, a provision was adopted, requiring IMO to review by 2018 the availability of 0.50 mm% fuel oil for use by ships, to determine whether the new lower global limit on sulfur emissions from international shipping should come into effect on 1 January 2020 or be deferred until 1 January 2025. At its 70th meeting, October 2016, the Marine Environment Protection Committee, MEPC, confirmed 1 January 2020 as the effective date of implementation for ships to comply with the 0.50 mm% sulfur content of fuel oil requirement. Furthermore, the IMO adopted in 2019 the amendment to MARPOL Annex 6, prohibiting the carriage of non-compliant fuel oil for combustion purposes, for propulsion or operation on board a ship, as of 1 March 2020. Annex 6 to MARPOL 7378 allows, however, for alternative technologies, methods such as scrubbers, which are at least as effective in terms of emissions reductions. The EU Directive 2016/802 of the European Parliament and of the Council of 11 May 2016 relating to a reduction in the sulfur content of certain liquid fuels also restricts the sulfur content of fuels used in the areas of their territorial seas, exclusive economic zone and pollution control zones to 0.50 mm% maximum as of 1 January 2020. The EU directive allows the use of fuels exceeding sulfur content of 3.50 mm% supplied to ships using emission abatement methods operating in closed mode. The EU directive also has set a maximum limit of 0.10 mm% on the sulfur content of marine fuels used by ships when at berth for more than 2 hours. Both MARPOL Annex 6 and the EU directive require a representative sample of the fuel delivered to be taken and retained on board, which, if necessary, can be used to demonstrate compliance with the sulfur limits. This sample, often referred to as MARPOL sample, is to be drawn continuously throughout the bunker delivery period at the receiving vessel's inlet bunker manifold. However, when this is not possible, e.g., safety aspects, it can also be taken at a mutually agreed location. The MARPOL sample shall be retained on board the vessel until the fuel is substantially consumed, but for not less than 12 months. Indiscriminate commingling of fuels can lead to stability problems of the final fuel due to incompatibility of the fuels used as blend components. Eventual problems, damages arising from the commingling of fuels are the responsibility of the individual who made the decision to commingle the fuels. Fuel suppliers guarantee the stability of the fuel they deliver, but cannot be held responsible for compatibility problems with another fuel. Rules of commingling safety. Segregate and do not commingle different bunker stems. If commingling is unavoidable, check the compatibility of the fuels in advance and make a final decision based on the test result. If a compatibility check is not possible, one component unavailable at the moment the decision has to be made, reduce the amount of one fuel to a minimum before adding the second fuel. Remember, generally, fuels of the same viscosity grade with similar densities will be compatible. The Joint Industry Guidance on the Supply and Use of 0.50% Sulfur Marine Fuel, published in 2019, provides additional information and guidance on avoiding incompatibility issues and minimizing the risks of commingling potentially incompatible fuels. The stability of a residual fuel is defined by its resistance to precipitate asphaltenic sludge despite being subjected to forces, such as thermal and aging stresses, while handled and stored under normal operating conditions. Compatibility is defined as the ability of two or more fuels to be commingled at a defined ratio without evidence of material separation, e.g., sludge formation. Stability reserve is defined as the ability of an oil to maintain asphaltons colloidally dispersed and to prevent flocculation of the asphaltons. Total sediment aged is an important specification for heavy fuels. Currently, nearly all heavy fuel is marketed with the stability guarantee of maximum total sediment aged, ISO 10307-2 0.10%. Stratification in heavy fuel oil tanks is minimal when this specification is met. SciMac, the International Council on Combustion Engines, has published a guideline on marine fuel handling in connection to stability and compatibility. This guideline aims to provide a practical and working understanding of the definition of stability and compatibility of marine fuel oils and how these two specific fuel properties may be best managed in the supply chain and onboard ships. It complements and expands on the information given in ISO PAS 23263-2019. Thank you for watching. For more marine engineering insights, go on chiefengineerlog.com.